Yes. So in the last session, we started binary tree, binary search tree. We discussed binary search tree also. Let us see how to create a binary search tree. For example, we have the numbers. We have the numbers like 43, 10, 79, 90, 12, 54, 11, 9, 50. So you will get the question like prepare a binary search tree with these numbers. Now you need to prepare a binary search tree. Let us take first one 43 here. Step 1, 43. 43 as a root node. And the next element is 10. You must remember the property of the binary search tree. What is that? Left subtree numbers, left subtree values must be less than the root node, and right subtree values must be greater than the root node. Here second value is 10. So root node is 43. So the 10 must be at the left hand side, right? So we created 10 here as a left subtree. Next one is 79. 79 is greater than 43, right? And that's why you create 79 as a right subtree for the root node 43. Then 90. 90 is greater than 79. So you must create a right subtree for the 79. After 90, you have 54. Okay. So you must be create as a left subtree for the 79. Next, 12. Come to here. 12 is less than the 43. Na? So you must come to the left hand side. And coming to the left hand side, we have one root node 10. Left subtree node 10. So 12 is greater than 10. So you must create a right subtree for the 10 and you can write 12 here. Then 11, 11 is less than the 43. So you must write at left hand side and we have 12 here. Okay. So 11 is less than the 12. So you must create left side for the 12. Okay. Next, 9 as per the question series. Next number is 9. So coming to here, we have 10 here and 12 already created right hand side. 9 is the less than the 10. So you can create a left subtree for the 10 and write 9 here. Next number is 50. 50 is greater than 43. You go for the right subtree. And coming to the 53 and 90. So 54, 54 is greater than 50. So 50 is less than 54. That's why you must create a left subtree for the 54 and place it in the left subtree. So this is the brief idea to you to understand how to create a binary search tree with the given elements. Now, next type of the tree is splay tree. A splay tree is another variant of binary search tree, which is also a binary search tree. It is another variant of the binary search tree. In a splay tree, recently accessed elements is placed at the root of the tree. This is the very important property of this splay tree. Let me repeat. What is the important property of this splay tree is in a splay tree, recently accessed element is placed at the root of the tree. So in the real time, suppose if you want to access some numbers, some node value very frequently, in such cases, those element is placed at the root node. Then we can access it easily. It takes very less time to access. So that's why the split trees are used in this case particularly. Split tree is a self-adjusted binary search tree in which every operation an element rearranges. Every operation an element rearranges the tree so that the element is placed at the root position of the tree. What is the element is being accessed very frequently, that will be placed as root or very near to the root position so that that can be accessed by taking very less time. With that, we can improve the performance of that particular application. In a split tree, every operation is performed at the root of the tree. All the operations in split tree are involved with common operation called splaying. What is splaying? Splaying an element means it is a process of bringing it to the root position by performing suitable rotation operation. As I said just now, what is the element or what is the node key value we are accessing very frequently? We are implementing splaying operation. What is splaying operation? Splaying is a process of bringing that particular node to the root position. To put that particular node as a root node, we need to perform some rotation operations. What type of the rotational operations we can perform? We'll see that. In a splaying tree, splaying an element rearranges all the elements in the tree so that splayed element is placed at the root of the tree. By splaying elements, we bring more frequently used elements closer to the root node so that any operation on those elements is performed quickly. That means the splaying operation automatically brings more frequently used elements closer to the root of the tree. Okay, this is we covered already. Now, as I used just now, we need to use some rotations in the tree to bring that frequently used element closer to the root position. We need to follow these following rotations. The rotations name are jig rotation, jag rotation, jig jig rotation, jag jag rotation, jig jag rotation, jag jig rotation. We are using two words with the different combinations, jig and jag. So these are the generally used rotations in the splayer tree. With help of the depending on our requirement, we may use different rotation. With help of these rotations, the frequently used key bring up to the closure to the root node. So this is the point you need to understand about these splayer trees. Now, next type of the tree is B tree. A B tree is different from binary tree. Binary tree is different. Binary search is different. B tree is different. In search trees like binary search tree, every node contains only one key or one value, and that contains a maximum of two children. We covered that in our last session, right? In the binary tree or any tree generally, whatever the trees we covered as of now, in that all the trees contains only one key, one value. One node contain only one value, and every node contains maximum of two children. Okay, but there is a special type of search tree. This is also a search tree. Split tree also a search tree. There is a special type of the search tree called B tree, in which a node contain more than one values. This is very important point. A unique point about the B tree. A node contain more than one values, more than one keys, and more than two children also. These two are important points about the B trees. Let me repeat. B tree is also a binary search tree. The important points about the B tree are it contains more than one values. Point one. It contains more than two children also. B tree was developed in the year 1972 by Bayer and McCreight with the name height balanced M-way search tree. Actually, the name of this tree was height balanced M-way search tree in the initial stages. They used this name, but later on, this name was renamed as B tree. Now we are using the name B tree. Before the B tree, they used the name, it was called as height balanced M-way search tree. So by depending on those two important properties, a B tree can be defined as a B tree is a self-balanced search tree. A B tree is self-balanced search tree in which every node contains multiple keys more than one, okay, and has more than two children. This is the definition of the B tree. Here the number of the keys. So here the number of the keys in node and the number of children for a node depends on order of B tree. How many keys a node has, how many children a node has depends on order of the B tree. So every B tree has an order, right? So this is about trees. Now you have sorting concept also. Let me come to these sorting techniques. As per your syllabus, we have, yes. So next we have sorting techniques. So as per your syllabus, we have insertion sort in that. So first thing is you must understand sort is nothing but you must arrange the elements in ascending or descending order. That is called sorting. You may get elements in unsorted manner. You must sort those elements either in ascending or in descending order. That is the sorting concept. Okay. We have different types of these sorting techniques like selection sort, bubble sort, insertion sort, quick sort, merge sort, bucket sort, radix sort, and so on. So as per our syllabus, we have insertion sort, radix sort, bucket sort. So we are going to cover those sorting techniques. Insertion sort works similarly as we sort cards in our hands in a card game. So generally we have an idea about the cards, playing cards. How we play the cards in the same way, we can sort the elements in the insertion sort. We assume that the first card is already sorted. The first card is already sorted. Then we select an unsorted card. Suppose in our hands, we have some cards. We assume that the cards, whatever we have in our hand are sorted already. We select an unsorted card. if the unsorted card is greater than the card in our hand. Okay. In the case, suppose if we have only one card in our hand and we have several cards on the table, and we are assuming that whatever the card we have in our hand is already sorted. Whenever we are pick up a particular card, we are assuming that the card in our hand is already sorted. For example, let us say in my hand I have the card 2, number 2 card. If I pick a 3 card, I need to place after the 2 because I'm assuming that 2 is already in the sorted position. Suppose if I pick card 1, I need to place before the 2 in my hand. Right? So same logic we are implementing in the insertion sort also. Insertion sort is a sorting algorithm that places an unsorted element at its suitable place in each iteration. In the playing card also, how we placed an unsorted card in its correct position, in its suitable position. In the same way, every time a element is placed in its suitable position, correct position in each and every iteration. So that is the logic, that is the algorithm we are implementing in the insertion sort. See the example, you can understand it easily with this. Let us say this is the initial array. We need to sort this element. I want to arrange this element in the ascending order. This is the input array 9, 5, 1, 4, 3, unsorted array, input array, right? Now, start your algorithm from second element because, as I said just now, we are assuming that first element is already sorted. We are assuming that first element is already sorted. Start with second element. Store this second element in a variable. Let us say my variable name is key. I stored this 5 in the variable key. Okay. Then I want to compare the 5 value with whatever the values we have before that value. We are working with second cell now. You must compare this value with 9. So 9 is greater than 5. So 9 must be placed at the second position. Then this becomes empty. Okay. This 9 is going to from this position to this position. This is vacated. So whenever it is empty, we stored this 5 in one variable key. From that variable, you must copy that value or store that value in the first position. So this is step 1. Let me repeat step 1. This is the given array. Assume that this is already sorted. You can start from the second cell. In the second cell, we have element 5. Before start the algorithm, you must store that element in a one variable. In my example, my variable name is key. I'm storing that value 5 in the variable key. Then compare this value, key value, with the cell which is placed before that, 9. 9 is greater than 5. So that must be moved to the next position. Now this becomes empty because 9 is moved to this place. Now you can store the 5 from the variable key to first cell. Now 5, 9. We have 5, 9. So this is the result from this step 1. 5, 9, 1, 4, 3. Next iteration, we must write a loop for this. Next iteration. This is already sorted. This is unsorted. Store this one in the variable key and compare first 9 with 1. 9 is greater than to 1. So it first move to the right hand side. Next, compare 5 with 9. 5 is also greater than 1. That is also moved to the right hand side. Then it will becomes empty because 5 is removed here. Now 5 is moved from this place to this place. So there is no 5 here. That is empty place. So from the key, store 1 in this place. Now this is the output after completion of second step 15943. Now working with next element 4. Store this 4 in the variable key. Compare the 9. 9 is greater than. So move to the right hand side. 9 comes here. Compare 5 with 4. 5 is also greater than. So 5 also must be come to the right hand side. And 1. Compare 1 with 4. 1 is less than. Okay. So don't move 1. Place in the same position. And when 5 is moved from this position to this position, it is an empty one. Right? So in the empty place, store the 4 value from the variable key into this second position. Okay, this is step 3. Next, working with the last element 3, store in the variable key and compare with 9. 9 is greater than 3, so move to the right hand side. 5 is greater than 3, move to the right hand side. 4 is greater than 3, move to the right hand side by 1 always. And compare with 1, so it is less than, so don't move, keep as it is. So whenever 4 is moved from this position to this position, it is an empty. There is no 4 here. So it becomes empty. So in the second cell, store the value 3 from the key and store here. Now finally, the list you will get is 1, 3, 4, 5, 9, which is in the sorting order. Okay. So this is the algorithm we need to follow for this. Clear, I hope. First, let me repeat it in brief. We must assume that first one is sorted. Take the second one, compare with the previous values. If the previous values are greater than the current working element, those must be moved to the right hand side. Otherwise, no need to move. And when you find a empty space, in that empty cell, we need to store that value which is available in the key. Where in the key, we need to store the element with which we are working in each and every iteration. So this is about this sorting technique. Let me tell you some more sorting techniques. Yeah. Next sorting technique is bucket sort. Bucket sort technique that sorts the element by first dividing the elements into several groups. Those groups are called buckets. First step in the bucket sort algorithm is first we need to dividing the given elements, the given array in simple terms, into several groups. Those groups are called buckets. Each bucket is filled with a specific range of elements. Depending on the range, we are dividing the elements actually. So each bucket is filled with a specific range of the elements. I will show you an example later on. The meaning of second element is, for example, 5 to 10 elements are stored in bucket 1. 11 to 15 elements are stored in bucket 2. Like that, depending on range, are 10 to 20, one bucket. 21 to 30, another bucket, so on. Like that. Okay. The elements inside each bucket are sorted using any of these suitable sorting algorithms or recursively calling the same algorithm. So we're dividing the given input into the buckets, and every bucket has range of elements. Those elements, what we have in the buckets, are sorted by using any one of the sorting algorithm like insertion sort, selection sort, bubble sort, and so on. Finally, the elements of the bucket are gathered to get the sorted array. So we have individual buckets now. Individual buckets elements are sorted. So we need to gather all the sorted array to make the final array. Bucket sort is mainly useful when the input is uniformly distributed over a range. Nothing but we have some elements in this particular range and we have some elements in this range. 10 to 15, 10 to 20, we have some elements. 21 to 30, some elements. Like whenever you have the elements, those are uniformly distributed over a range, then the bucket sort is mainly useful. For example, you have 10 to 10, only one number, then 1000 to 200. Like that, if you have very long gap, in such cases, bucket sort is not suitable to implement. See this bucket sort algorithm implementation with help of the example. This is the given array. The process of bucket sort can be understood as scatter-gather approach. Okay, we are scattering the elements first. After sorting that, we are gathering that. That's why we can understand it like a scatter and gather approach. The elements are first scattered into the buckets, then the elements of buckets are sorted. See, for example, we have 5 buckets here. In the first bucket, we need to take the elements which are in the range of 0 to 5. See now 0 to 5 means only one element. The element 1 will be stored in the first bucket. Right? Next, 6 to 10, not 5 to 10. Actually, this is 6. 6 to 10. Identify 9, 8. In the same order, 9 will be stored first. After that, 8 will be stored in the second bucket. Then 11 to 15. 11, okay. 11 to 15. 11 will be stored. 13, 12. Same order. Okay, 11, 13, 12 in the third bucket. Like that, 16 to 20 elements will be stored here. 21 to 25 range elements will be stored. So we have 5 buckets. In the bucket 1, we have 1. Second bucket 9, 8. Third bucket 11, 13, 12. Fourth bucket 17, 19. Fifth bucket 21, 24. Now, by using the any sorting algorithm, we need to sort these buckets individually. This is one element, no need to implement. We have 2 elements, implement any sorting algorithm, need to sort that. After sorting, 8 to 9. 11, 13, 12. We can use any insertion sort, bubble sort, whatever it might be suitable. You can use that sorting algorithm and that will be arranged in the sorting order 11, 12, 13. This is also same 17, 19, 21, 24. After sorting. And finally, the elements from the each and every bucket will be gathered in the same order. 1 from bucket 1, 8, 9 from the second bucket, 11, 12, 13 from the third bucket, 17, 19 from the fourth bucket, 21, 24 from the fifth bucket. Now you observe all the elements are sorted. Okay. This is bucket sort. Clear? So this is one more example, but you go for any one of the example, that is enough. Then what is worst case complexity of the bucket sort? When there are elements of close range in the array, they are likely to be placed in the same bucket. Obviously, right? This may result in some buckets having more number of elements than others. So it makes the complexity depends on sorting algorithm used to sort the elements of the bucket. The complexity becomes even worse when the elements are in the reverse order. Suppose we are taking elements in the buckets. All the elements are completely in the reverse order, not in ascending order, for example. So obviously that takes more time. That is the worst case. Best case. It occurs when the elements are uniformly distributed in the buckets with a nearly equal number of the elements in the each bucket. We have 5 buckets. In the 5 buckets, we have 10, 10, 10, 10 elements. So that is the best case. The complexity becomes even better if the elements inside the buckets are already sorted. So we are taking the input array. We are storing the elements in the buckets and equal range of the elements we have. And in that, again, the elements are already in the sorted. So that is very best case complexity. That takes very less time for us to sort because already probably sorted. If insertion sort is used to sort elements of a bucket, then the overall complexity in the best case will be linear. That is order of n plus k. Order of n is the complexity of making the buckets. In order of n plus k, order of n is the complexity of creating the buckets. And order of k is the complexity for sorting the elements of individual buckets using the algorithm. Right? So finally, the complexity for the best case is order of n plus k. So this is the best case. Next sorting technique is radix sort. Radix sort. Radix sort is the answer. The idea of radix sort is to do digit by digit sort starting from least significant digit to most significant digit. So the main idea of the radix sort is we are going to sort the digits, sort the numbers digit by digit, like ones position sorting first, tens position, hundreds position, like that, position by position. Radix sort is a sorting technique that sorts the elements by first grouping the individual digits of the same place value, then sort the elements accordingly to their increasing decreasing order depending on the place value. Suppose we have an array of 8 elements. First, we will sort the elements based on the value of unit place. First, we will sort the elements based on the value of unit place. Unit place digits will be sorted first. Then, we will sort the elements based on the values of 10th place. Second step, 10th place. And this process goes on until the last significant place. This is the algorithm what we follow in the radix sort. So see the example. With the help of the example, the radix sort will be clear to you. Let us say this is the input. Okay, input array. Input array is 10, 10, 21, 17, 34, 44, 11, 654, 123. This is the given array, input array. Now, how to sort these? Using radix sort. Based on algorithm, we will sort the input array according to the ones digit, units place first, least significant digit. Observe, first write the digits like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And write the digit here or write the number here. In which number you have the unit digit 0. Observe here. This is 0th row. Na? We are talking about only unit place, ones digit. Write the number here. In which number you have 0 in the unit place. So how many numbers we have here? Only one. That is 10, where we have 0 in the unit place. So I am writing 10 here. Now, second row, 1. Write the number or numbers here in which you have 1 in the ones position, 1 in the units position. If you observe the given array, we have two numbers, 21 and 11. These two numbers where we have 1 in the ones digit or unit place, 21, 1, 11, 1, which is highlighted with red in color. Right? So write 21, 11 in this way. Next, identify the numbers in which you must have 2 in the unit place. If you observe all the numbers, we don't have any number in which we have 2 in the unit position in the ones digit. So no need to write anything. We don't have any number having 2 in units place. No need to write any number here. Next, come to the 3. Write the number in which you have 3 in the unit position, ones position. Only one number we have, 123. So write 123 here. Next row, 4. What are the elements we have in which we have 4 in the units position? 34, 44, 654 also. Unit position, right? Next, coming to the 5 and 6. Observe here. We don't have any numbers where we have 6 in the unit position, 5 in the unit position. So no need to write any number. Then 7, only we have one number where we have 7 in the unit position. Then coming to the 8 and 9, we don't have any numbers where we have 8 and 9 in the ones position, right? So this is the step 1. What we have done as of now, we have an input array. As a step 1, we are writing the numbers where we have 0 in the ones position, 1 in the ones position, 2 in the ones position, and so on, 0 to 9. So the array becomes, now after completion of writing this, write the new array like 10, first one. Next, 21, 11. Write in the same order, 21, 11, then 123, 123. Like that, write these numbers in the same order, 34, 44, 654, 70. Now see, I have written those numbers in that order. Output of the step 1 becomes the input to the step 2. Now, next step is write the digits same like this 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now identify the numbers in the array, in this array. Okay, in this array, where we have 0 in the tens position. 0 in the tens position. If you observe, the 10 position numbers are highlighted with blue color. There is no number 0 in any number. There is no digit 0 in any number. So no need to write any number here. Then observe all the numbers where we have 1 in the tens position. 10 because 1 in the tens position. 11, 1 in the tens position. 17, 1 in the tens position. Next, come to the row 2. Identify the numbers where we have 2 in the tens position. 21, 2 is the tens position. 123, 2 in the tens position. Next row 3. Identify the number where we have 3 in the tens position. 34. For the 4, 44, 4 in the tens position. For the number 5, 654 because 5 in the tens position here. If you observe the array, we don't have any numbers where we don't have 6 in the tens position, 7 in the tens position, 8, 9 in the 10th positions. We have these numbers only finally. Now, write these numbers in the same order. 10, 11, 7, 21, 123, 34, 44, 654. So I have written same numbers in the same order. Right? Now, next step. Write 0 to 9 like this, same as the previous steps. Identify the numbers where you have 0 in the hundreds position. Okay. So actually, we have only two numbers, 123, 654, where we have 100 position, right? In the remaining positions, we don't have 100th position. They have unit and tens positions only. That's why we need to add a 0 before the remaining numbers. The numbers we don't have 100 position, we need to add 0 before those numbers. So if we add 0 for the all the numbers other than 123, 654, because we have 100 position for those two numbers only. You can write all those numbers in this row by following the same order. 0, 10, 0, 10, 0, 11, 0, 17, 0, 21, 0, 34, 0, 44. That's it. If we add 0, the value won't be changed. We know that. Then 100 position number is 123. So write 123 here. We don't have any numbers where 100 position is 2, 3, 4, 5. Coming to the digit 6, we have one number where we have 6 in the 100 position. That is 654. Write that number. And coming to the 789, we don't have any numbers. Okay. Then write these numbers in the same order again. 0, 10, but I'm writing 10 only. 10, 0, 11, writing 11 only. Okay. 0, 17, 17, 21, 34, 44. After that, 123, right? 123. After that, 654. Now observe these are sorted. 10, 11, 17, 21, 34, 44, 123, 654. All these are in the sorted manner, right? This is how to implement radix sort. So you can observe one point here. As we have 100 position in the given array, we have 3 steps. Until completion of the third step, when you complete the third step, all the elements will be sorted. If we have a 4-digit number, that takes 4 steps to sort. Okay. Then, what is the running time complexity of radix sort? Since radix sort is a non-comparative algorithm, we are not comparing the elements like insertion sort, selection sort, right? This is non-comparative algorithm. It has advantages over comparative sorting algorithms. Let there be d digits in input integers. Radix sort takes order of d into n plus b. Okay, where d equals to number of the cycles. In the given example, 3 cycles, na 3 steps. And b is a b. B is the base of the number system. B means whatever the example we covered, that is a decimal number system related example. So the base for the decimal number system is 10 only. We know that. Okay. N is number of the uh, numbers, how many numbers we have in the input array. D means how many digits we have, maximum number of the digits. B means base of the number system. So that's it about this session. So let me recall in brief what we covered. In our session, we covered split trees, binary search trees. We started with binary search tree. We have seen how to create a binary search tree. And how to create a binary search tree step by step depending on the values of the node. Start with a root node and less values of the root node must be placed at the left hand side. greater value than the root node must be placed on the right hand side. Based on that, we can create the binary search tree. After that, we covered splay tree. The main intention of these splay trees is if you have the requirement to access a single element or very few elements very frequently, then you can use splay trees. Very frequently used elements created as a root node or nearest to the root node, then we can access those elements very quickly. After that, we covered B trees. B trees, the unique properties. As of now, whatever the trees we covered, we have only one key in the every node. But coming to the B trees, that has more than one keys and that has more than two children also. This is the unique properties of the B trees. Later on, we started sorting techniques. Okay. And in that, we started with the sorting technique. Insertion sort technique. Insertion sort technique is just like a play card game. You must assume that one card is already in the sorted, and you must assume that remaining cards are not sorted, and you must take one card and put in the correct position in the sorting order. By following the same logic, we can sort these. This is about insertion sort. Coming to the bucket sort and radix sort. In the bucket sort, the given array is divided as a different type of the different number of the buckets. In each and every bucket, we are storing some values depending on the ranges, and every bucket elements are sorted individually. After sorting, they are collected or gathered to give a final output. This is bucket sort. Coming to the radix sort. Radix sort is a sorting technique based on the place values. First unit place values will be sorted. Then tens position values will be sorted. Then hundreds position values will be sorted. After that, all will be combined together to give the final output. So it is basically sorting techniques on the place value of the given numbers. So this is about today's session. In the next session, we cover some more points about sorting techniques and some collections of the Java and some more trees also.